Okay, in the last lecture, uh, we talked about F manifolds and femboid donuts. So the F manifold, which is a structure, which is something that goes like this. In its topology, such that that is homeomorphic to N. It's a element, and it's a subset of R. So we're talking about the femboid manifold and the femboid donut, which formally is called the 2F manifold FT2. 2F manifold FT2 FLT2. So the F is for the femboid, and then the T is for the torus notation. Well, of course, the FT2 is described via this atlas. First one, F x squared minus F y squared plus F z squared equals F r squared or 1, such that these guys, which just talked about, so basically psi are set F or femboid or universal femboid set cross itself. Well, I'll just do dot 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 here until equals F r 2 squared, such that these guys are part of M. Such that FR2 is greater than FR1. So that's F FR2 is greater than FR1 squared. Okay, so that's it's hot today. So that's what we discussed in the last video or the last lecture. So I'm not gonna delay this further. We're gonna do a re-examination of the Stephenson-Maxwell paradox, the Kirov-Argyle paradox, and Hilbert's femboid. So what we're gonna do now is we're gonna talk about them in the context of our femboid group, our universal femboid group. So that's that. Okay. Okay. So you guys recall that this not exactly the femboid group that I said in those videos are not exactly what I told them. Like rotations of an object or a set of rotations. That's not how it is. But rather it's a structure containing the sets of rotations as a sort of thing. Okay, as a as constituents of the underlying set of the structure. So right. So now we're gonna correct that, or rather we're gonna make it much more clearer by defining our own femboid group that's an actual group. Okay. So we have some class of femboids, and then we have an operation that we can perform on them. And then from there, we're going to sort of apply some theorems to show that they're not necessarily good. So, yeah. So this is going to be our theorem 3, our third theorem of this course. I know we don't have much theorems in this course, but there's this. So it's here also. So theorem number 3. Theorem number 3. So now I have the paper that I need the notes for the proofs, because I'm also gonna state the proofs for it, okay? Because you guys can't just derive the proofs on your own. It's gonna be a bit difficult. It requires the axiom of choice. I mean, at this point, you're supposed to know about the axiom of choice and have some experience working with it, considering we require set theory to before discussing about topology. But I'm still gonna use the axiom of choice here. It's very important. Okay, so um, okay, so one of the main axioms or fundamental assumptions of ZFC was the axiom of choice. Now I talked about this in my position theory course, the axiom of choice. And the axiom of choice is what it states is that given a bunch of choices, there's at least one possible choice for each option. So, like I said in position theory, if I have these two markers over here, there's only exactly one option for each. So I can, if I want to choose this, there's only one option for, or one choice. Either I pick it or don't pick it, right? So that's our choice. So that's choice. So there's a function that assigns this thing. So formally, we say that for any sets AB, for any sets AB with a binary relation, B, it's a subset of A cross B. For all x inside A, for all x inside A, there exists a y inside B. There exists a y inside B that satisfies B of x, y, such that, or which implies that, okay, so let me rephrase that. If we have that for x, for all x inside A, there exists a y such that these both satisfies B of x, then there exists an f that maps A onto B. What else? A into B, such that for all x inside A, such that for all x inside A, B, x and the image of x under F, or the image of A under F, satisfies this formula. This wind is so bad right now. Us, we're looking hot today. So it feels good. Like it's a very simple, like a sweat. Okay. Oh Jesus. Okay. So that's that. And the thing is, the axiom of choice here is very monumental when it comes to things like the Buttock paradox. And we use the Buttock paradox to sort of prove, or we use a strong version of the Buttock paradox to essentially remove or extract a certain characteristic of our group, and then say that, oh well, the group is intrinsically independent of that characteristic. So let's say H. We let H denote homosexuality. Well, it's part of every femboy in our group, right? What we essentially do is express every femboy as some sort of set inside it. Of course, they are sets after all, with that thing. And then what we want to do is extract the H, right? So we can say that, well, every femboy, or we can state that every femboy has H in it, right? So what our goal is in this lecture is to extract that H, remove the H, and then show that, well, every femboy inside the group is just the same without the H, right? So that's what we did in the lecture concerning the actual paradox itself. The reason why we call it a paradox is that, well, the thing is, we showed we essentially showed that something is equal to something that's not itself, right? So we essentially proved that x is not equal to x, or well, x being any number you guys can think of, right? So that's what we proved then, and that's why it's called a paradox, because yeah, and that's why the Buttock paradox is called a paradox, because obviously we cannot cut up a ball, right, or a shape, and then reassemble those pieces to get two copies of the same thing, right? We cannot do that. If we try to construct two pieces out of those two copies of the ball out of those pieces, we get smaller balls, or we get a Lebesgue measure that's lower, or that's less than the Lebesgue measure of the original shape. That's why it's called a paradox. And so that's why the shapes that we're talking about here are not Lebesgue measurable. Okay, so here's when we sort of split apart this femboy group that we're talking about with the other femboy groups we've been talking about. The other femboy groups that we've been talking about, especially manifolds or topological spaces constructed from F, Bactal F, are Lebesgue measurable. We can measure them. we can fill them up with finitely many small femboys and then say, oh, well, there are this many femboys inside, or they can be measured through this many femboys. But the thing is, when we start grappling with the concept of infinity, right, and when we start talking about infinite amount of femboys inside a group, right, it starts the line starts to blur between what seems impossible and what logic tells us, right? So this tackles upon the very philosophies of mathematics. Okay, so so like in the video, we're gonna first take a detour into geometry, basic geometry, and then of course we're gonna discuss the necessary group theory, especially the proof, and the Buttock Schroeder. Uh, wait, hold on. I mean, we're gonna codify equidecomposability through group theory, and we're gonna discuss the Buttock Schroeder Bernstein theorem. That's a very important theorem here, especially for the Vanitas Paradox and the strong form. Okay. So that's that. So the Buttock Schroeder Bernstein theorem, right? So that's after discussing about some geometry. So first we're gonna talk about equidecomposability. Now with a better understanding of the topic, because I'm more mature now when it comes to these things. Okay. So okay. So we generalize the notion of volume, surface areas, and uh, areas basically as things we call measure. And a measure of an object is, well, what value you get when you measure it. So say if you have a straight line, if you have a straight line going from this point onto this point, we have a measure, which D, that maps this entire thing onto Rn. So that's the formal definition of a measure. So definition 5, I think. Just check my lecture notes to see if this is our fifth definition. I don't want to get you guys confused here. So oh, 6. Okay, definition 6. A measure D or a metric is a between map between a set A on to R1 space. So essentially, what D does is associate members of A to a number, a real number. So yeah, this makes sense because when we assign, say, sides of a square, right? We get the sides. We grab the sides of the square R. We could say R. We get a measure for the area to be R squared. That's one possible version of D, or that's one version of the morphism of D here. D can be equal to the area, and then the area's formula is given via R squared. That's a measure. Or if we're given a cube and we want to find the surface area, it's 6R squared. Or if we want to find the volume of a cube, it's R cubed. Funny thing. That's why they're named cubes in the first place. So that's what. Oh, cold water. Okay, so now what we want to do is retrieve the notion of equidecomposability. First, I need to make sure you guys can see this. You guys can see. Okay, so what equidecomposability? First, let's talk about decomposability. So, a given set is decomposable if we can split it into a finite amount of pieces. So here we have some m here, which is the midpoint, which is a plus b over 2. Okay, so what's the midpoint is a decomposition of this. Okay, and we can say that this line here, AB, is decomposable. Okay, so likewise, if we have a certain square, right? If we can cut it up into finite many pieces, and such that those pieces are the best measurable, then the square is decomposable, finitely decomposable, right? Now, equidecomposability is a notion where if we have two objects, okay, we have two objects that seems so different, right? They seem so so not like each other, but it turns out that there is some map or morphism we can perform between them two so that they are the same. So it's not the it's not the homeomorphism in the case of in the case of topology where we squish them or something like that or morph them, but rather what we do is we cut them up. Okay. So what we do is we we grab the shape and then we cut it up into finitely many pieces, and then we can rearrange them into another object. If we can do that between these two objects, or two objects in on question, then the two objects are what we call equidecomposable. Likewise, if we can deconstruct this object, this marker, into this, or if we break this down into pieces and rearrange those pieces to get this eraser, then we can say that this is equidecomposable with this. So if those two condition holds, if we can deconstruct each of these guys into each other, or deconstruct them and rearrange them into each other, then these two are equidecomposable. Okay, very simple thing. And the thing is, the interesting thing about equidecomposability is that this is what the Greeks used back then to prove things about geometric figure, about areas of geometric figures. So this is actually a method used by I believe Pythagoras to prove the Pythagorean theorem: a squared plus b squared equals c squared, by essentially cutting up a square and then proving that it's somewhat analogous to a uh, to a triangle. Sorry, my brain stopped. Brain farted. Okay, so yeah. So the formal way of saying this, okay. So the definition here in my notes is we say that two polygons are congruent by dissection if they can be dissected, ignoring boundaries, onto the same finite number of polygonal pieces, which can be put into correspondence such that each pair of corresponding pieces are congruent. Okay, so that means the isometry. So isometry the plane sends one to the other. Okay, yeah. So if we have two objects A and B, and then we have some metric defined over there with alpha small a and small b. If we have some active isometry between A and B, then these two guys are uh, equidecomposable. So also B, there's some isometry between these two measures, A and B, and B and A. So if that's the case, then A and B are equidecomposable. Okay. So basically, we can cut up A and then we can cut up B. And if we rearrange those pieces, right? If we have those pieces, rearrange those pieces, they would have the same area essentially, or volume, or measure, whatever you call it. Okay. So that's equidecomposability in a more in-depth manner. Yeah. And it's obvious to say, it's obvious to show that two figures that have the same area or same measure are equidecomposable, or are congruent via dissection, right? So if we have a square that has r squared, or let's say area 2 square meters, and if we have another square of area 2 square meters, then they are immediately congruent because we can cut up one piece and then fit it into the other piece, or we can cut up one figure, the first figure, and then rearrange the pieces to get the second figure. So that I believe it's a very intuitive concept at this point. And we can go further to there. Okay. Okay, so um okay, so let's just talk about covers, shall we? In topology, covers are basically it's a copy of the set. So it's a collection of subsets of a given set, such that the union of the subsets are the set. So a cover, definition says that a cover of a set A of X. A cover of a set X is a finite union, or a finite collection, of subsets, say mu alpha, alpha and j that's inside X such that the union, the general union of these guys, alpha and j of mu is inside or is precisely X. Okay. So that's a cover. So it's basically a copy of X that's composed of its subsets. Okay. So say for example, this part right here, it's composed of the main body itself and its cap. So if we show these guys or express these guys as subsets and then we take their union, we have a cover of this entire marker. Oh, very much. Okay. Now, um, now if we want to generalize our intuitive notion or abstract our general notion of decomposability with polygons or figures, we say we're going to use this definition here to make our eighth definition. Definition 8. Okay, so definition is eighth definition. Okay. So definition 8. Two sets A, B, or I say X, Y. That's just the subsets of Rn are equidecomposable if their covers are equivalent. Okay, so like how we express covers as sort of breakdowns of a given set into unions or the breakdown of a set into unions of its subsets, right? A cover. Now we say that if we're able to break down X and Y into their covers, and their covers are the same, they're essentially equidecomposable. Okay? So it's now an abstract notion. It's not just about breaking down a figure now, but rather it's about breaking down sets or partitions. It's not a general thing, right? So it can not only apply towards figures, but other things like maybe mathematical structures, maybe formulae, or just mathematical objects in general. We can do this, or this will hold true so long as their covers are equivalent, right? Now, yeah, in the context of the paper here, our definition 8 is two subsets A, B inside Rn are equidecomposable if they could be partitioned into the same finite number of pieces, which can be matched such that each pair of corresponding pieces are congruent. So, okay, so let's use shapes again. So let's say a line. So X and Y are inside all one. Say two lines here, which I will call X and Y. Let's divide X and Y into two pieces of equal length. Now, if these two pieces are the same, right? I'll make a copy of these things. So I'll make another one here. That's the same thing as X. But this time, instead, I'll say that this is 4 divisions. Or, yeah, 4 divisions now. If these guys over here, this, let's say A inside X and B inside Y, or B equals Y and A equals X. If A and B are equal, then surely X and Y are the same. So if the partitions of X and Y are the same, or yeah, rather than the same, then we are saying that X and Y are the same. Okay? So yeah, we still have a lot to go here after this. But it's important that you guys know about equidecomposability because that's the main premise of our theorems. Theorems 1 and theorems 2 and 3. 2, 3, and 4, and well the corresponding next theorems. Okay, so now what we want to do is talk about Lebesgue measure. So I keep saying, well, the same Lebesgue measure. These things must be Lebesgue measurable and stuff like that. But the thing is, not all sets are actually Lebesgue measurable. As we will come to see, our femboid group that we will partition here. So I'll call it, well, F, different pen, different marker. So I will call F, um, FH, a group with its topology. As you will see, as you will come to see, this structure over here is not necessarily Lebesgue measurable. When we discuss about the Kirov-Argyle paradox, we will see that this is not Lebesgue measurable compared to FT, FH, TF, or the regular universal femboid group, which is Lebesgue measurable. Okay, so in order to understand Lebesgue measurable, we're going to discuss it. Okay, so what is a Lebesgue measure? So this is a way of formalizing or making rigorous our notion of measure, basically. Okay. So now our goal with the Lebesgue measure is to divide a shape or sort of, you need to assign a measure such that one, an n-dimensional hypercube of side x has measure xn. Two, the measure of union of finitely many disjoint figures is the sum of their measures. So we can break down a figure into the measure, or the measure of a figure into measures of the subsets of the figure. And yeah, and it's finite sum as well, okay? So we can do something like Xenos Paradox. So yeah, now as I stated, the best measure is not for all sets. There are going to be some sets like, well, the structure I just said now that are not the best measure. So that's that. So we say that a set B is the best measurable if the following equation is true. So if we let okay, so definition 9. Definition 9. For any subset, the consequence side R2 define lambda star of x to be the infimum inf of all k inside the interval 0 to infinity. Such that x is equal to such that x can be covered by a countable set of hypercurves of general different figures with total measure k. Okay, so given this set here and then another set, you say that a subset y of R2 is the best measurable if and only if, okay, so the infimum of B, this infimum of the interval that's yeah, basically this thing over here, is equal to the infimum of this here, of the intersection between A and B, plus of the infimum of K, such that, well, this set here can be covered by a countable set of figures. And then now here, this time it's B, the complement of B and A. So this time B without A. Because there's gonna be the case we're in. I'm actually not in. It's actually X and Y. Sorry, this X and then that's Y. Sorry, that's what we. This is X Y, and then this is X. Okay, so we can split up this infimum into the sum of two infimums of K, infimum K, such that the intersection between X and Y can be covered by a countable set of figures, and then this complement here can be covered by a finite set of figures with a total measure of K for each guy. So the least number in this interval, we can. I'm not sure if it can be zero. I'm pretty sure it can be zero. It can be just, well, we have nothing, right? And then we have the best measure zero for something that's nothing, right? And we have a best measure for we have some non-zero the best measure for an object that exists like a square. Okay. Okay. So what's that? Okay. So the interesting thing about definition 9, which is about the best measure, is that our Kirov-Arga paradox is a shortcoming of this definition over here. Because as we will come to see, there will be a set which is, well, F, should be F, H, oh, not that, sorry, it's supposed to be not valid M, H, that is not the best measurable. So yeah, that's the thing about this definition 9. Okay, so on to definition 10, or the next part of my lecture. Okay. Beat today. Okay. All right. Now that we've talked about the best measure, we will take a detour into group theory. So now, so that we can construct the Banach-Tarski paradox in R3 or our Kirov-Argal paradox in R3, we will first want to go into group theory. So okay. So this involves orbits. Okay. So so you guys check out my Femmy lecture on that. So FEM episode 2, I believe. So about orbits. I already discussed about that. Okay. So if let's say we have a group G, okay? If G acts on X, we said that the subsets of X, A, B, are G decomposable if they can be partitioned into the same finite number of pieces, which can be matched such that each pair of corresponding pieces AI, BI are related by the action of some GI in G. So some symmetry in G or some element of G, such that B sub I is equal to this G sub I, this action applied on the subset A. Okay, so we basically show that two subsets are equally decomposable with respect to a group action. Yeah, if we can partition them, or if their pieces are equally decomposable. So, or we can express one of them, right? One of the subsets as the group or one of the elements of the group acting on the second subset. So, right, we have our A and our B. And then we have our group G, which has some element G, GI. Any element you guys can think of inside the group G. Well, what our 10th definition is saying is basically B and A, G equally decomposable if and only if B is equal to G sub I acting on A, and A is equal to G sub I acting on B. So if we apply this on all the elements on A, we would get B. If we apply this on B, we get all the elements in A. So now we can think of this this action G sub I as cutting up A, right, and then rearranging them. So when we apply this function on A or this mapping on A, we get B, and then vice versa. That's our 10th definition. Okay. So an example of this is putting into correspondence. Let me sit for a while. An example of this is putting into correspondence elements of the integers by defining some morphism, right? So we have our basis element or our neutral element or identity element E, right? And so we just need to right. So what we want to do is our next goal. Not sitting down. Our next goal is to show. Okay. So now let's make a demonstration of this definition. So now what we want to do is correspond the integers to natural numbers. That's what the book here. I'm the notes here saying. Okay. So now, in order to put these two into correspondence, we need to show that these guys are G equidecomposability. G equidecomposable. To say, well, this is corresponding to this, or these guys have a relation here. And okay, so we're gonna say that this Z is our A, and then this N is our B. What is our G? What is our G sub I? How do we put Z into corresponds to the natural numbers? Well, we can express natural numbers really as the union of all even and odd numbers excluding zero. So excluding zero. So now, okay, so what's our first step? Our first step is to extract zero from Z. Or rather, we're gonna extract, we're gonna remove, or rather, no, not really extract or remove. We're gonna extract the odd and even numbers from Z. Okay. So follow me closely here. So now, B, we know that B over here, B is equal to, B is our natural numbers, is equal to the union between even and odd numbers. Or even numbers 2, 4, 6, 8, dot, dot, dot. Factors of 2 basically. And the odd numbers are 1, 3, 5. Numbers that are not divisible by 2. Okay? So we can express this as a union of these two guys. So natural numbers. And so now, we also know now our G sub our correspondence to set this with respect to Z is basically what we're gonna say now is B is equal to or rather I got it mixed up. Okay, so yeah, B is equal to A union the negative part of the or the positive part of the integers. Okay, so what we're saying here is that what B is basically is, or the integers is basically saying that the integers is just equal to the union between the natural numbers, which is A, and the negative portion of the integer. So minus infinity up to -1. So basically saying that's what it is. So positive integers or negative integers here, which is minus infinity up to 0, right? Is we're gonna union that or combine that with A, which is just our natural numbers, and then we get the integers. That's what we get. So now, our bijection or our G sub I is equal to some morphism, which maps some even number E. Okay, sorry. We're gonna map basically N onto the even numbers, and that is done via this. So G, or rather E, some even number or some number N is mapped or fixed onto N divided by 2. and that's via G sub I. And then for the odd numbers, talk about n here, the even natural numbers, and then now G sub I maps n O, which is the odd numbers, onto E by this Morpheus. So it fixes n, G sub I fixes n onto 2n minus 2n plus 1 over 2. And so that's an example of our tenth definition about decomposing sets and then rearranging them to become each other. So we essentially express these guys, we express the integers and the natural numbers as their covers, and then we show that their covers, if some functions applied on them, would become the other cover. So yeah, that's an example of it. Now to get a more in-depth example, we want to examine free groups. What are free groups? Well, I thought about free groups on this course already, but basically speaking, what a free group is a set. A free group is a set of all. Oh, it's a group. Sorry, it's a group. It's a group of all words on the generators of a set. Okay, so combine. So the set or the group of all word sprinkle concatenations of the generators of a set A. So the elements of the set A, if we combine them in many ways possible, take the set of all those combinations of them, we get the free group over A, wherein the operation of our free group is the multiplication or decomposition property. It's a general property of blocks. So we have some concatenation over here, or rather, increase the operation over A, and then we have this operation, this stand-in for the operation plus, minus, so long as it satisfies the group axioms, or makes it such that this structure satisfies the group axioms. Okay. So yeah, that's a free group over it. Now this is gonna be a bit tricky to discuss, We should Crisp is about to go off and you're gonna hear some noise. Okay. So now we consider free group G, which is equal to some F, or the ordered group. Okay. Okay. Now consider the group G equals F cross 1R, such that R squared equals 1, acting on itself, where F is the free group on two generators. So maybe a cyclic group of order 2, then F cross 1 is G equidecomposable of all of G. Thus formally, one copy of F is equidecomposable with two copies of F. So what we're essentially saying is that F is the same as two copies of itself. If F is a free group of some group of generators, and we showed that, or it was shown through, Now, to prove that theorem, call it theorem 3. I'll write it down here. Theorem 3. F cross 1 is equidecomposable with F. And the proof for this requires what we call the Buttock Schroeder Bernstein Theorem. Okay, let's start again. Let's stop staring. Okay, so the Buttock Schroeder Bernstein Theorem states that suppose a group G acts on a set X. If each subset of X, A, B, is G equidecomposable with a subset of the other, then A is G equidecomposability with B. Okay, so we're essentially restating our definition 10 a while ago. Okay? We're essentially restating definition 10, but in a more formal way. We have some group action that acts on a set X, and then we have two subsets A and B of X. um, these two are equidecomposed with each other, right? Through G. Okay. So okay, if they're G equidecomposed with each other, then we say that those two subsets are G equidecomposable, right? So okay, it's gonna be a bit heavy. Actually, okay. So I think I already discussed the proof of this. I know I said in the beginning of the video that I'm gonna say the proof, but to be honest, I need to conserve my the ink for my markers. Uh, so as much as I want to, as much as I want to discuss the proof here, I really can't because we're running out of resources right now. We're in the process of getting new markers. Don't worry. So maybe I'll post a follow up video on the proof. So yeah, that's so a proof of theorem two follows after we construct a proof for the Buttock Schroeder Bernstein theorem. So I'm gonna skip the proof because I already said the proof. I already discussed the proof in the video about this. So yeah. So now, okay. So there's not a theorem, theorem four, which states that there exist some rotations of a unit sphere, so a sphere of radius 1, in R3, so yeah, a shell from the S3, that are independent, i.e. non-trivial word, that corresponds to the identity rotation. So um, each guy, each element of the set, or of the set acting on the sphere, right, or rotations acting on the sphere, do not correspond to, or there's no word on them that corresponds to identity. Okay, so that's what that the theorem, our theorem four is saying. Yeah, theorem four. And I think I already discussed that as well. If not, I'm gonna do a follow up. Okay, so now let's construct the Vanitas Paradox. So let's do it. Okay, I'm getting my rest. I start with a full icy cold glass of water after this because it's very, very hot out. Okay, theorem number 5. Theorem 5. Okay, the set FH, not count FH, is EP decomposable with, okay, FH without the element H. H is the gay characteristic. Okay, so let's consider now. Okay, okay, let's consider now that let's consider that FH. Let's consider FH is composed of a collection of Femboy sets, which is acted upon by H. Okay? So let's start with uh, H, and then or rather okay, let's say that H is some central object, right? So H is somewhere over. Okay, so uh, okay, so we have some. Okay, it's a bit hard to explain. Okay, so we have some rotation, right? So now we're abstracting into shapes. So we're now thinking of this femboy set as a circle, S1, where an H now is the center. Okay, so H is some central object, right? So some sequence of H's, some sequence of H's, right? Say that for infinite amount of gate people, right? And then, so now what we want to do is embed a circle inside here. So we make a bunch of points and then run the circle for them. Okay. And so these points are basically just H and then H squared, H cubed, but we're gonna assume that some of them are not gate, right? Okay. So what we do now, oh, So what we just did here is that we extracted the H element from each femboy inside this set. So we're not gonna sort of show explicitly the femboys of the set, but we just show the H that we know are part of each. And if we just make this disappear, then they're essentially gone from the femboy sets inside this femboys collection or class here. So what we want to do now is apply some rotation or some function that sends this onto h squared onto h cubed, and then so on and so forth. So basically, we need to find some. We will find some rotation of this circle, right? This point here. There's embedded circle. Let's see if you can see that. There's embedded circle such that the center disappears. So what we're essentially doing is we're cutting the circle up, right, into pieces, and then what we're doing is making each point that divides the circle go to the next one, such that one of the points is essentially nothing because it just completely wraps around itself, right? It just continues moving on and on and on to infinity. So it was essentially as if that point never existed. Okay, so we want that rotation to be something like sigma. So sigma. No sigma. Okay, so if we apply sigma on this entire thing, we would get sigma h squared dot dot dot. What sigma does, sigma fixes some hn onto hn plus 1. And so once we apply this rotation, which basically rotate the center, right? And then we make the center go to this point, and that would go to that one, and then so on and so forth, travel in the circle. It's essentially as if we remove h. H is not there anymore. So this is the proof here. This is a picture proof, but understand this is essentially what it is. We basically apply some rotation on an embedded circle inside this S1 for both of them, boys. And then we showed that the center is not part of it. Oh, as I said, it's actually very heavy today. I ended up having to sit down for more than 2 times already. Oh, and that's what it is. It's essentially the circle going on itself. And that is the theorem of Argyle paradox over there. Now the Stephenson-Maxwell paradox. The Stephenson-Maxwell paradox it's actually just a stronger version of the Buttock paradox. So yeah, I understand. I know I'm supposed to discuss it here. I will. I will. Okay, so we're gonna gloss over some other stuff now. I believe are not necessary here, but I think that we get. Okay. Yeah. So there's a lemma after this one. There's a lemma after this one that basically states that. Oh, let's find that. Ooh. There's a lemma next that states that our S here, our S1, not really S2, right? Well, you can say it's S2. You can say it's a sphere instead, right? And then we just have some other sphere embedded over here, and then we rotate that sphere such that the center goes away. And there's also a bunch of other steps where we're going to take away some other troublesome points, which we call D. So yeah, what we basically did we remove some troublesome points that makes our theorem collapse, and so we end up with the Vanitas paradox. So we just combine our techniques of rotating and then also our Buttock Schroeder Bernstein Theorem and all that stuff to show that the unit femboy ball would be B2, B3, I think B3 or B2 is equidecomposable with 2 copies of itself. So we cut it up using the Buttock Schroeder Bernstein theorem, and then we apply this rotation here to remove the troublesome points. And then we apply those cuts again, and then use the axiom of choice to reconstruct the ball into 2 copies of itself. So that's the paradox there. So likewise, we're able to a stronger version says that we have 2 bounded sets inside Rn. Then those 2 sets are equidecomposable. So if we let one of the sets be some femboy set here, which has an intrinsic value of T game here, or being a femboy here, and we have some T set, a set T, right? That are part of Rn. Let's say Rn. They're both part of Rn. These two are equally decomposable. Okay. So and they're notice they're non-empty. Okay. So this F and our hypothetical transgender set are not empty. They should contain the empty set. Uh, but the theorem six, I'm not gonna write it down anymore. But theorem six states that they are both equal. So the femboy is a transgender, transgender is a femboy, and yeah, that's where the controversies start happening. I hope you guys can see my post right now, but because oh boy, was it a controversial theorem indeed. Theorem six here is it was very controversial. When I stated it in a couple of Discord servers, I was branded as transphobic because I essentially proved using mathematical logic that a femboy is a transgender person, a transgender person is a femboy, and I essentially pissed off two parties at once, right? Uh, kill two birds with killing two birds with one stone. Am I right? Oh dear, what's that? But there are actually some positive theorems that I derived out of this actually, including Hilbert's femboy. And Hilbert's femboy is just basically, well, we just show that, well, we already know this, we already proved it, right? We already have the proof of the Buttock Schroeder perspective. We already have the proof for the theorem of Argyle paradox. And we already have the proof for the Stephenson Maxwell paradox. All we have to do is just extend the proof to any set, right? Any set, and then we're able to essentially show that it is something else, right? So likewise, Hilbert's femboy is some set that is equidecomposable with an infinite amount of H's inside it. So the amount of gay sets inside it. And so that's Hilbert's femboy essentially. So we just extended this concept. We extended this concept into more sets such as the femboy, and then show that well, it is equidecomposable or equal to copies of its gay set. And then so it's an infinitely gay thing, and then that's basically theorem 6.1 to 6.3. So you can sort of just state it on your own and then find it out, or just revisit the video. So yeah, sorry to cut this video a bit short and gloss over some important stuff or other stuff. You can check out the paper concerning this. It's by Anders Kasior, uh, 18504 Seminar on Logic, and it was published during May 17th, 2007. And of course, don't forget to check out the Vsauce video on the Vanitas Paradox about cutting up a chocolate bar into pieces and then rearranging such a piece, such that we get one extra piece out of thin air. It's an amazing thing, but it's a trick altogether. And likewise, it's a great demonstration, a physical demonstration of Vanitas Paradox about seemingly getting something out of nothing. So cutting up a pea and then ending up with something as large as the sun. That's what this is all about. Using these contradictions, we're able to prove that femboys are essentially not gay. Not gay, and we also prove that, well, transgenders are femboys, and that's not such a good theorem now, is it? But hey, there's no theorem out there that's not controversial, you know? I mean, if you have a theorem, eventually there's going to be those people who say, hey, the theorem is offensive! It's offensive, it's shit! It's bad! It's bad you made the theorem, and it's bad you made a proof for that theorem. But it's mathematical logic, or it's math in the end of the day, and well, it's undeniable. And I say again, I keep saying this, but all these things are for mathematical playfulness. They're not here to attack any sort of subset of our community. Okay, these theorems and their proofs were not made to offend people. These were just made for the sake of jokes and mathematical playfulness. You know, practicing math and teaching guys a little bit of this stuff along the way. So I know I keep saying that, so I'm just gonna stop. I'm gonna stop stalling further and just say, well, okay. So the last lecture, which is about the bussy space, or at least the last lecture in our original course outline. So maybe like all other courses, we're gonna add more lectures here, depending on the change in shift or the shift in the subject. So now, after this, after the last lecture, it's gonna mark our fourth complete course in LOSC. So I don't know. I still have I still have three more courses to discuss. The first one is Gender Theory 1, and second was Gender Theory 2. And the last one, before I complete my work here in LOSC, is gonna be relationship theory, and that's also a relatively new course, like this course, Femboy theory and position theory. All of these courses are new, to be honest. We established LOSG just last year. Just like, but I'm not sure if Professor Lando actually established Ligma University much earlier than LOSC, or um, yeah, we did establish LOSC later than Professor Lando, because this is inspired by his channel. My persona is actually based on his persona. Uh, but we take his lectures to the next level by sort of making courses out of them in mathematics. And if you check out my Twitter, I have a Twitter, by the way. You guys can check it in the. It's in my profile. Um, it says there on my bio that I'm a professor of general mathematics here at the Lyceum of St. Canis. And what I mean by professor of general mathematics, or what we mean by professor of general mathematics, is that we teach more than 2 or 3 mathematics subjects, right? Or we are instructors in more than 3 mathematics oriented subjects. So Chorology 3A Femboyology is a mathematics oriented subject, and position theory and femboy theory are also mathematics oriented subjects. Also, regicalculus is a mathematics oriented subject. So since I taught more than 3 now, or I'm teaching more than 3 mathematics subjects, I am considered a professor of general mathematics here at LOSC. I know that's probably not how things work in regular universities. Well, if you're a professor of general mathematics, you're teaching some form of general mathematics. So like a little bit of calculus, a little bit of vector calc, a little bit of analysis, a little bit of real analysis, a little bit of group theory, a little bit of abstract mathematics, a little bit of applied mathematics. That's a general mathematics. But here, general mathematics is referring to teaching more than 1 or 2 or 3 mathematics subjects. So yeah, again, I'm gonna stop stalling this lecture. I'll see you guys in the next one, and that's gonna be our last lecture for this course.